Well, doing that, I forgot when I talked about the small modular reactors, another thing to keep in mind about the Fukushima incident is it's pretty clear even at this juncture that the close spacing of the 4 reactors that got into trouble and to some extent the interconnections and common systems got them in, potentially got them into more trouble. And certainly explosions and nuclear debris from some of the explosions, from reactor X compromises activity in reactor Y. Now, in the context of SMRs, the plan is to build these, maybe start and build one, but build them in 4 packs or 6 packs with fairly close proximity. There is discussion about shared systems. There are even discussions about shared control rooms, which the Japanese didn't go to. And if you start having troubles, with operating 6 reactors and 1 or 2 get in trouble in a control room and the control room has troubles, then what happens here? This is an ongoing discussion with the Nuclear Regulatory Commission, but there are some implications there. Okay, let's talk about some fuels. What do you want this fuel to do? One, it's to maintain its physical integrity, to contain the nuclear fuel and to keep the fuel in position. You don't want it moving closer to fuel next to it or too far away or anything else. The fuel has to be compatible with the coolant. You want the contents of it to have a minimum adverse impact on neutron economy, be able to transfer heat, allow for control, and maybe facilitate extended storage and disposal. I don't think that certainly current LWR fuels or HTGR fuels were conceived with disposal in mind, but maybe going into the future it might be useful to at least keep it in mind a little bit. First I'm going to talk about metal-clad fuels, water reactors, and then sodium-cooled reactors. Graphite-based fuels, I'm going to focus on the block, and I may get to the pebble or not, we'll see. The effect of irradiation on the fuels, and some on spent fuel characteristics. And then depending on how timing's going, our fearless leader will make a call on what we do next. And this, I'm going to talk about PWRs first, and talk more than a little from this cartoon. This cutaway of well, let me start from the right. The basic component is a fuel rod or fuel pin. Can be called either thing. Occasionally you'll see in some literature that this component is called a fuel element, but I call this a fuel element or fuel assembly. In any case, what you've got is a long Zircaloy tube about maybe the size of your little finger, maybe it's a tad smaller than that, thin-walled. And Zircaloy is an alloy of zirconium with a little bit of tin and a little bit of iron, but it's like 97% zirconium. You weld a plug in the bottom, you put a spring in here because when it heats up, the fuel will expand and contract and you want to keep it together. Then you put in a stack of fuel pellets, uranium dioxide in the current designs, and then you have another spring at the top, and you put weld another Zircaloy plug in this thing. And these rods are on the order of 12 feet tall. So they're not hardly self-supporting by any means. But then what you take is what are called 2 end pieces, sort of looking like this. And the end pieces are usually made out of something like stainless steel 304. And you take a whole mess of these rods and you group them in a square array, and you put them in as what is called a grid spacer, which is one of these dealies here. There's a number of them up and down the assembly, which is just basically a sheet metal square with little pieces of sheet metal making it into a crosshatch, where you end up with all these little cells, and you put rods through on the order of 85–90% of these in a regular kind of an array, and then in the holes that you don't put fuel rods, you put these gizmos, which are called tie rods. And this is just a hollow Zircaloy rod that is threaded on the end. And so you take that entire array and you set it into the bottom plate, and you put a nut on the thread so it's held onto the plate, and then you put the top end piece on, and again you put this top nut on, and you end up with this kind of a structure, a fuel assembly with the guide thimbles. And the guide thimbles provide, a few of them have instrumentation. It also provides a place for the control rod entry in this particular design. This thing has about 460 kilograms of uranium and about 135 kilograms of hardware. And by hardware, I mean the cladding, the grid spacers, and the end pieces. Grid spacers in older designs were Inconel. Now they're going to Zircaloy because of its better neutron economy. The array here depends on the manufacturer, but something like a 14 by 14 to 17 by 17 array of rods. Enrichment in the 3 to 5% range these days, with toward 5% being much more dominant right now. And to some extent, I'm going to describe the PWR as it was maybe 5 or 7 years ago, and then some of the recent advances. But that's basically a pressurized water assembly. These are what the fuel pellets look like. And the overall assembly is nearly 4 meters. And again, there can be some variation in that. These are uranium dioxide fuel pellets, and you notice the dishing in the end. And assuming my memory lasts, I'll talk a little bit about why that is done when we get a little bit further on. This is a picture of one. It's very tall, and even with all the rods grouped together, it's still, I mean, you can't latch onto one end of this and sort of lift at the other end like a long pole. And so they're lifted from the top where they're strong, and they're treated and shipped very carefully in foam rubber, or not foam rubber, but shaped packaging, because by the time you get the value of the uranium, the enrichment, and the fabrication in this, you're talking really serious money here that is the worth of these. Now talk a little bit about the boiling water reactor, and a little bit about difference by difference. The basic concept is the same. You've got a square array of fuel rods. They're in Zircaloy clad. They're about the same length, and they've got grid spacers on them and end pieces to hold it together and all that kind of stuff. They do not have the guide thimbles or tie rods. I'm sorry, they do have the guide thimbles and tie rods, but there are a couple of differences here. One you can probably see right off the bat, and that is this sheet metal thingy here, which is variously called a fuel channel or a fuel shroud. And all that is just a sheet metal can going around each fuel assembly, made out of Zircaloy again. And the reason for that, in a boiling water reactor, they want to, in order to control the steam generation and the nuclear reaction, they want to keep the water that enters the bottom of the assembly in the assembly, even if it's turned to steam, and not let it spread out laterally to other assemblies in a somewhat unpredictable way. So that's what that fuel channel does, basically, is it keeps the water in this particular assembly. Secondly, PWRs do not use control rods. They use a control blade, and you see this array of 4 assemblies. And if you imagine, 4 boxes set beside each other, and they're spaced apart a little bit, and the control, I can't call it control rod, the control plates is shaped like a cruciform, like a cross, and it slides in between, vertically up and down, between those 4 fuel assemblies outside of the fuel channel or the fuel rod. And again, those come in from the bottom, and those cruciforms just contain tubes full of boron carbide, which is the poison used here. These assemblies are smaller than PWR assemblies. generally 180 kilograms of uranium, maybe 110 of hardware, about the same length. The fuel element ray is 8 by 8 to 10 by 10. Traditionally, the fuel rods have been slightly larger diameter than a PWR, maybe 25% larger or something like that. The BWR fuel management and fuel design has traditionally been more complicated than that of PWRs. PWRs, pretty much a rod would have one enrichment of uranium, although an assembly might have multiple enrichments, but each rod, they might have a little bit of burnable poison, which is a sort of like a borosilicate glass rod they would put in some places if there was very hot fuel around to help control the nuclear reaction. But that was about it for PWRs. These reactors, they would mix gadolinium or gadolinia, another neutron poison, in with the UO2 in variable concentrations. They would have variable axial concentrations of uranium enrichment, so more complicated because, as you might recognize, at the bottom you've got 100% water with its moderation. At the top you've got a fair amount of void from the steam, so you've got a very different neutronic situation, and they've gone to that to help them balance out the nuclear reaction and the power peaking in there. Power peaking being important because you've got safety limits and you're limited by your hottest rod and your hottest point. So to the extent you can flatten everything out, you do better. Now, fuel variants here, we're getting more up into what's happening right now and where they think they're going. They're developing advanced cladding, especially for the PWRs. One alloy called Zircaloy, which is sort of a US kind of an alloy. They're putting a little bit of niobium in that to help it last a little bit longer. The French have developed one called M5 that they're working with. They've had a little bit of trouble here with it recently, but claim to have fixed it. They're also looking at duplex cladding, where you've got an inner layer that's a little bit more for strength and then an outer one that's a little bit more for corrosion resistance. And so those are being looked at and still under development. The BWRs just seem to be tweaking the Zircaloy composition, not going quite that far. There is some potential and some research being done on making clad out of silicon carbide, which is a ceramic, as opposed to the metal cladding, in the hopes that it will be more corrosion resistant and maybe allow higher temperatures. Also, there's a move in both cases, BWRs and PWRs, to go to smaller diameter elements, and they're looking at annular elements, which is something along this line, where you got the fuel matrix, sort of this dark stuff in here, and then you've got cladding on the inside and the outside. And you see some pictures of some of these prototype things. And also this is silicon carbide, a so-called duplex silicon carbide cladding with a composite on the outside and a silicon carbide monolith inside. The purpose of the annular thing by allowing is to enhance heat removal. I'll talk a bit more about this later, but uranium dioxide isn't a great conductor of heat, and so there's a very steep temperature gradient. Well, let me put it this way: the center of a fuel rod is much, much hotter than the part out near the cladding, and that causes a number of structural and materials performance problems, again, that I'll elaborate on. So this annular pellet is designed to alleviate that. Other variants, mixed oxide fuel. This conventionally, historically, has been meaning instead of using enriched uranium, you get yourself a bunch of plutonium and use that to make up the required the fissile requirements. Typically talking about, depending on the burnup you want, but uranium dioxide containing 5 to 8% plutonium dioxide is common, at least at the start, although some designs have gone up higher than that. The U.S., I say already being done, that's probably an over-exaggeration. The U.S. has a plant, there's building plants at Savannah River to, one, convert plutonium pits and other plutonium forms, purify them enough so they've got the plutonium in hand, and then to fabricate, use that to fabricate spent fuel to be irradiated in a power reactor, produce its energy, and then be managed as a waste. So that's ongoing in the U.S. In other countries, the French and the British are actively recovering plutonium and making at least some of it into spent fuel and irradiating that fuel. Although the recovery goes on in those countries, some of the plutonium is owned by other countries. So you've seen some of those assemblies, like in Belgium and I think Switzerland, have seen these going into reactors. So it's not really a big deal, although there are some tricks to it, but it seems to be in hand. There's some discussion, haven't gotten to the reprocessing talk, but future reprocessing, there's a lot of impetus, I guess I'll call it, to not separate a pure plutonium stream, but to separate a uranium-plutonium stream where the uranium and plutonium remain together, and possibly to have the neptunium mixed in with that. And doing that and making it into a mixed oxide fuel seems to be a fairly modest extension of what we're doing now. Some discussion about whether we want to put americium and curium in. They're a lot more of a challenge in many directions, in many dimensions, being heat generators, neutron generators, and having not nearly as nice of ceramic chemistry as uranium and plutonium. So that's being thought about, but their challenges remain. More PWR fuel complexity. The more recent designs, like the BWRs, are starting to have enrichment gradation within a rod. They're also starting to include burnable poisons mixed in with the uranium dioxide, and even an axial blanket. And what that is, if you imagine this rod, and let's say the fuel enrichment is, for most of the rod, is 4.5%. They might put the top few inches and the bottom few inches and have those pellets be 2.5% enriched or something like that to help with the neutron economy. So their new designs are headed in this direction. It used to be they were a lot more forthcoming about all their designs, but everything's proprietary and competitive now. Finally, there is the possibility of thorium oxide in the thorium fuel cycle, which tends to do better in thermal reactors than in fast reactors for the most part. There isn't a lot of interest in this country in doing it. To have that fuel cycle make sense, you just about have to be doing reprocessing to get the uranium-233 out, and reprocessing is contentious enough on uranium fuels, and going here, just not much interest. Is some degree of interest in other countries, in particular India has some, seems to have a fascination with it, maybe because their uranium reserves aren't very large, but they have a lot of thorium in the form of these monazite sands, sort of rare earth sands, and places where they have very interesting background radiation levels, I might add. Metal-clad, metal-cooled, easy for me to say. This is a typical kind of a fuel assembly for a sodium-cooled fast reactor. And I'm sort of going to describe the historical variation on it, and then sort of where things might go in the more foreseeable future if they can make that reactor work. But this reactor is, and this is the top here. This is the bottom, and it sort of sets in a lower plate inside the reactor in a hole sized for this. And what you've got is I'll call it a fuel region, and this is it's often called the driver. It's the fuel that makes the reactor go, that goes critical. It's generally on the order of 20–25% plutonium dioxide, Again, the higher plutonium because fast and the cross sections are lower, and we talked through that. And the rest would be uranium dioxide. And then in the traditional design, you have axial blankets, just like I mentioned for the light water reactor, although quite a bit longer, or longer in both cases. And those would be composed of natural or depleted uranium dioxide, no enrichment. And some other features here. This, like the BWR, has a fuel channel around it. The construction here is stainless steel. The cladding, the channel, the whole mess is all stainless steel. The rods can be spaced apart by grid spacers, as in the PWR and BWR. There's also designs, it's called a wire wrap. You basically tack weld a thin wire at the bottom of a rod and wrap it around spiral and tack weld it at the top, and those keep the rods separated and allow the sodium to circulate. Do I have anything else to say here? Let's move on. And this is one design, one core layout where you've got fuel sort of in this region with some control and that kind of thing. And these reactors, in at least the historical incarnation, have radio blanket assemblies. Not only uranium dioxide on the top and bottom of the driver fuel, but assemblies composed entirely of uranium dioxide pellets surrounding it. And the idea here historically was for neutron economy. For any neutron that wanted to try to leak out of the driver fuel region, make it a good chance it's going to get captured by the uranium dioxide and make plutonium. And because it's a fast reactor and that fission to absorption cross-section thing I talked about, these reactors can be net breeders or makers of plutonium. And on the order of 20 to 30% seems to be achievable with these with proper designs. In other words, you come out with, say, 20% more plutonium than you went in with. And the idea was to get enough of that extra plutonium, then you start up another fast reactor because you need a fair inventory for that initial driver fuel. Now, that's the historical incarnation. More recently, especially in the U.S., there hasn't been a lot of interest in breeder reactors and having a lot of plutonium. There's an awful lot of plutonium in the world in storage at this point. And there's been a fair amount of discussion in the Department of Energy concerning, well, gee, maybe it'd be a good idea if we were processing to take these actinides, and not just plutonium, but neptunium, americium, curium, make them into fuel, put them in the reactor, and fission them into shorter-lived fission products, and gee, help the repository and do other nifty things like that. So what's going on? What you would want to do is you don't want to be breeding more plutonium than you're consuming if you're trying to destroy actinides. So now there's a lot more look at reducing the breeding or conversion ratio. Instead of like 1.2, make it 0.75 or 0.5 by eliminating these fertile material blankets that I mentioned in favor of a non-fertile neutron reflectors that just would bounce back a neutron. And in the limit, going to an inert matrix fuel. Instead of having UO2, have plutonium in zirconia or yttria or some other thing. These are not without challenges because as you take the U-238 out of these systems, you start to encounter control and safety issues. And there are likely limits to where you can go with this. Also, the first point up here, the designs of these reactors are not settled. There is, I guess some, I don't want to call it consensus, but sort of coming together on what an assembly might look like, broadly speaking, but how many you put in the reactor and fueling patterns have fairly wide variation. Also, historically, these reactors had dioxide fuel. There's an entire separate scheme that is a metal-fueled reactor. And you'll hear, I think, a good deal more about that tomorrow morning. but where instead of oxides, it's plutonium and actinide metal with some zirconium making up the fuel rod itself, and using pyroprocessing as opposed to aqueous processing. Finally, I mentioned the metal here. There's also some work going on in carbides and nitrides. They are a challenge. They offer some advantages in terms of heat transfer, but you cannot make carbide and nitride fuels in an oxygen atmosphere. It's got to be inert. And making these has proven to be a significant challenge, even by trying to make a handful of them by experts in a laboratory, let alone production. So there remain challenges, but those are the focus of R&D at this point. Now, graphite-based fuels. You saw the picture before, sort of over in here, of what this is the fuel assembly looks like, but I wanted to start at the bottom and sort of work up in this case. The fundamental component of this is called a trisoparticle. I think it stands for tri-isotopic structural oxide. Oh, I had it up there. I guessed right. And I have no idea what that means. A materials person probably does. But you start out with a very small spherical particle of uranium dioxide, most likely in the current designs. And then you put some coatings around it using some porous carbon to provide a space for fission products and this kind of stuff, fission product gases. Some silicon carbide, which is fairly impermeable, and a pyrolytic carbon layer to yield one of these particles, and that's the so-called triso coating. And these particles look like this, and you get an idea with the pencil point how large they are. They're extremely small. And before, when I mentioned fuel reliability issues, there's a lot more art than science in exactly how do you make these things with the coating to have the right integrity. It has been done and is being done, but it's not a slam dunk. What you do with that then is you mix it with some binders, just some well, pixie dust and this kind of stuff, some carbon and graphite, and you press it into this thing called a compact that's about that size. And then you center the compact. You heat it up to, I don't know, 1400 C or something like that, which drives off some of the volatile materials and sort of densifies this compact into a ceramic-like thing. And then you see this fuel element over here and all sorts of holes in it. And you'll notice a few big holes and then a lot of little ones. And you put these compacts in about half the little holes. And then the two end compacts don't have any fuel in them. They're just graphite and that kind of thing to hold everything in. The other half the holes, the small ones, are left empty because that's where the helium coolant circulates. And the big holes are where the control rods go through. For not every assembly will have control rods in it, but that's where the control rods go through. And this is sort of an engineering drawing of the thing. And the hole in the middle is where some kind of a tool comes down, and that's how the thing is picked up and moved around. And the core of this reactor, I think you saw the picture before, but it's basically just a big stack of these things. In other words, you don't pull out a whole stack of these, but you put a block on top of a block on top of a block. And at the outer areas are just graphite blocks that are reflectors. They don't have any fuel at all. But that's what the reactor design looks like. Now a little bit on spent fuel characteristics. First, some basics. Burnup is a measure of how much energy a unit of spent fuel is produced, generally measured in gigawatt-days per metric ton heavy metal or megawatt-days, some multiple of that. And the gigawatt day is the thermal energy, the heat produced by the fuel, and usually that you start with specific power, which comes from your reactor design, times the number of days the fuel is in the reactor, times the percentage of full power on those days, if it's not 100%. And metric tons heavy metal, by convention, heavy metal is thorium plus uranium and plutonium, neptunium, americium, curium. And the heavy metal, it doesn't include the anion like oxygen. And it's based on what was initially present in the fuel assembly. Even though you might burn 5% of it to fission products, still the basis of spent fuel is the heavy metal in the initial fuel. A rough rule of thumb, 10 gigawatt days per metric ton, you fission 1% of the heavy metal in the fuel. The effects of neutron irradiation, you see elemental and isotopic composition changes. The actinides fission to produce energy, and they produce fission products in mass amounts essentially equal to the actinides you produce. The mass equivalent of the energy is just round off error in this whole thing. And so if you get to 50 gigawatt days per metric ton, which is fairly common these days, your spent fuel is going to be 5% fission products, having the distribution that you've come to know and love, I trust, from that curve. You also produce neutron capture products. U-235 captures a neutron to produce some U-236. That can go on to make neptunium. The U-238 leads to plutonium, americium, and curium. If you're operating in a thorium cycle, you get U-233. Also, you get neutron capture in the hardware and fuel matrix, activation products in the Zircaloy, stainless steel end pieces, as well as the reactor hardware itself, the core barrel, and even the pressure vessel. You see a lot of physical changes: fuel swelling, cracking, clad embrittlement, fission gas release up into the plenum, and I'm going to talk a little bit more about that and elaborate that here in the next few slides. First, on burnup. How much burnup and where are we now? The light water reactors are now at the 40 to 50,000 gigawatt day per metric ton area, across a fairly broad spectrum of reactors, not just individual ones. They're pushing it ever higher, but there are limits there. To some extent, there are limits on materials. You can only push the cladding so far, and you start running into problems, and you start getting more and more failure rates. The failure rates have been gotten down to very low levels, but there have been recently, I mentioned with some of the M5 cladding, they started to spike up, and so these new advanced ones will still have some learning curve. Secondly, there's an enrichment challenge. Fuel cycle facilities for uranium enrichment, fuel fabrication, transportation casks, any place where you're handling this enriched uranium, was designed to a limit of 5% enrichment based on criticality considerations. You have to have some upper bound to know how much to keep things separated and whatever. And the fuel enrichments, which the print's probably a little bit small over here, but in this one, each one of those curves depicts the enrichment, and you're starting to push right up at 5%, which means they're going to have to change the licensing basis of this thing or get new casks. So there's a little bit of a wall there. It's not insurmountable. It's not a fundamental problem. You can design to any number you want. It's just the infrastructure is sort of geared to it right now. Other reactor types into the future, fast reactors, and the graphite-fueled reactors hope for 100,000 megawatt days plus. Some of these SMRs are just all over the map, from fairly conventional burnups for PWRs and BWRs to some of the other designs that they're wanting to push out way into the hundreds of thousands. So I think take that with a grain of salt or two. Now the in-reactor effects of burnup. First, you have a very steep temperature gradient that I mentioned before, where the cladding surface, is around 350 C, which is the temperature of the cooling water in the reactor. Zircaloy isn't much of a heat transfer barrier. But the center line is up at like 2300, so it's a very steep gradient. This leads to fuel pellet deformation. The fuel pellet tends to want to assume an hourglass shape, where it's narrow in the middle and then two sort of ridges or rims around the top and bottom circumference. The hourglass can dig into the cladding, leading to weakening and potential rupture. It can also lead to fuel pellets hanging. In other words, they sort of expand when they because of thermal, when they're hot, and then if you cool the reactor down, the edges will dig in, and so you end up with gaps between the fuel pellets, which again isn't good for your reactor control. And I mentioned the dishing before. The dishing of the fuel pellets is to help alleviate this. This is sort of the idea on the hourglassing, and so you've got these interactions between the fuel and the the interaction of the fuel itself, just because of thermal effects. The heating also leads to cracking, and you see this is a axial cross section and a radial cross section, and you see these cracks, which allow some volatile species to be released to the gas spaces in the rod, and maybe a little bit of hydrogen, and some of the semi-volatiles like cesium, and because of the chemistry, molybdenum can be a little bit volatile. Now that was sort of fuel pellet. This is fuel clad. As the radiation continues, Zircaloy cladding becomes increasingly brittle with burnup. It's not so bad when you're at power because it's fairly warm, and at that temperature the Zircaloy is reasonably ductile, but and at that temperature it can have a tendency to sort of collapse onto the fuel pellets. And sort of collapse in. When you cool off and get to room temperatures, then the brittleness can become more of a problem and is more pronounced because you get into the brittle temperature range. You've got neutron-induced embrittlement just from dislocations, but for Zircaloy, the more important problem is hydrogen or hydride embrittlement. Zircaloy corrodes on the outside, corrodes very slowly in water, releasing hydrogen, which migrates into the Zircaloy and makes these hydride deposits, hydride precipitates, at grain boundaries, and that causes the brittleness. And internally there is hydrogen, there's a little bit of ternary fission stuff, there's some tritium in there, and all of that is sort of working from the inside. And of course, as the more burnup you get, the more pronounced this effect becomes. And this is one of the issues in this extended spent fuel storage business, having to maybe go out a long time because we don't have a repository, is how brittle are they, how long how long can the cladding last, how long can it last and be transportable instead of, I'll call it shattering, but having something bad happen. And there's a lot more unknowns there than there are knowns, but those are the kinds of questions that are being asked and why they're being asked. Again, our old friend, the fission product curve, and just throw this up to remind you there's a whole bunch of different elements produced inside the spent fuel pellet, whereas you started out with a fairly pure chemical of uranium dioxide. And this table sort of takes the elements and groups them by their chemical behavior. And you can see here represented everything from, you've got noble gases with the valence state of 0, valence of, well, -1 here and all over the place for technetium, +1s, and you get up to here +2s, and then maybe +3s and some 4s depending on the exact chemistry. So you're introducing a whole bunch of different chemical species interacting with the uranium dioxide and doing things to you, and they don't do the same things to you. This is sort of a very quick summary of where things go. Noble metals, and here's some of them. They tend to exist as the metal in here, not as an oxide or something else, and they tend to precipitate at grain boundaries, which gives you fuel pellet embrittlement. Others tend to form stable oxides in the pellet, which give you swelling, and that's sort of depicted over here. Cesium and molybdenum tend to be volatile at the operating temperature, and some fraction of those migrate out to the cladding. The noble gases, not nearly all of them, but a significant fraction also migrate out. And if you'll remember the rod design, you had the springs in the top and the bottom, but of course a spring isn't solid metal, and there's a lot of void space up there, and that's where these gases collect. And as you go through the cycle, they tend to pressurize the rod a bit more than it started out with. I should say the rods, when they're made, they are pressurized with helium before they're sealed up to help with heat transfer. And okay. The fission products affect the oxidation state of the fuel, and the general net result of all these complex interactions is the uranium tends to be headed in the more oxidizing direction, which affects the fuel pellet integrity and the melting point and this kind of stuff. And there's some indication in the little table there of probable valences. And I already mentioned this, except the point on these noble gases don't help the thermal conductivity any. Helium's a lot better than these two guys for conductivity. And if you get a hole in the cladding, then these things tend to become bubbling out pretty quickly. Buildup of actinides. I referred to some of this before, but these curves, this is sort of a generic buildup curve, whereas your U-235 is going down, the total plutonium and the other isotopes are coming up or staying pretty level. When you reach the end of life, depending on the burnup, roughly 60% of your fissions are coming from plutonium as opposed to the U-235. The U-235 is about shot. Some of the activation products in your structural metals, for the ferrous alloys, you'll have some nickel, and you get nickel 59 and 63, some cobalt 60 usually. From zirconium, you get zirconium 93 and 95. These are medium to long-lived radionuclides. Cobalt 60 is the shortest at 5 years. In the coolant, of course, water coolant is the tritium, and sodium coolant, I mentioned the sodium 24. And then there's trace contaminants. You can have tramp uranium in your stainless steel or zircaloy and other structural metals. The uranium produces some small concentrations of transuranics, generally not very large. Nitrogen produces carbon-14, was mentioned earlier. The lithium and hydrogen produce tritium, and those two can be both in structural materials and the uranium dioxide matrix itself. Composition, I think probably done that. You end up at 33,000 megawatt days per ton, 3% fission products, 1% U-235, 1% plutonium, and the rest is your uranium-238. Plutonium goes up a little, and U-235 goes down a little if you get up to near 50,000, and of course the fission products get up to the 5% kind of an area. So after all this happens, you've got this complex mixture of elements that you got to consider first in separations as you go on downstream. The fuel and cladding are physically degraded, and some of it may have failed, and for failed fuel, it's canned when they get it out of the reactor. You put it in a sealed can and a lid on it. It's not just in the pool, spent fuel pool exposed. And you've got greatly increased radioactivity. Photons like gamma rays and X-rays, neutrons, alpha particles, beta particles. Generally, well, depending on where you are, the last two may or may not be a problem. If you're handling a spent fuel assembly, you probably don't care about alpha or beta radiation because it won't penetrate, and you've got to worry about the gamma rays and the neutrons. If you're in some parts of chemical processing, then you may have to worry about those because of what they do to your reagents. But the implications, you need radiation shielding, materials damage, and I think you're going to hear a good deal more about that. Thursday morning? I don't know. And a talk later on, there's one about that. And decay heat, for spent fuel in particular, it generates far more decay heat than you're going to get rid of by natural convection or conduction if you get any amount of it together. So you've got the spent fuel pools are one solution. They go on for a while until it gets cool enough. Then dry may be okay, but you've got to worry about all this routine and accident. I'm not going to talk about this because you're going to hear far more than I can tell you. Radioactivity of PWR spent fuel, just a couple of points on this. You've got a couple of major players. One is basically your strontium-90 and cesium-137 that are going away with about a 30-year half-life and going down to nothingness in 300 years or something like that. And then you've got your actinides, which start out somewhat lower, at times generally 70 or 100 years, start to cross over, and the actinides tend to dominate, americium-241 being your major player, and some of the plutoniums kick in. And then finally, when you start getting out to ridiculous long times, the decay daughters from the uranium in the fuel, U-235, U-238, especially the 238 because it's most of it, start to build in terms of activity. And in point of fact, if you carry this out far enough, there's these comparisons of uranium ore activity to spent fuel. You'll actually see the uranium come back up and those curves will merge, because after you go through all this trouble, you've only affected a few % of it, and on a graph you just can't see the separation because you still got most of the uranium.
Well, you're talking about different types of radioactivity, because initially you got a lot of gamma, right?
Yeah.
And then with the uranium, plutonium stuff, you got alpha.
Yeah, the radioactivity profile changes with substantial drops in gamma rays after 300 years because of the cesium-137 in particular. Right. The actinides build in with, or stay longer, I guess is the better statement, with alpha emitters, and there are some that have a significant or noticeable amount of gamma. It's not like cesium-137, but they have a significant amount of that. Americium-241 can be sort of nasty, and a few neutrons floating around there. And then in the very long term, the uraniums, because the half-life is so ridiculous long, it's just not. I mean, it comes back up, but it comes back up to a low level, if that makes any sense at all. And again, it's not much penetrating radiation at all there. They become that material becomes an ingestion issue if it is an issue. Also, these I put a couple of other things in here. This is decay heat, again for PWR fuel. You see very much the same trends. That cesium, strontium, and then the actinides dominate, and some of the other contributors here. And this is one where the actinides are assumed to have been taken out by reprocessing or something, so it heads for the basement really quickly. Okay, I'm at backup. Oh, great wizard. What now?
I think that you've had a long day, and it's time to call it a day. We have a heavy dose of nuclear engineering, and I recommend we reconvene tomorrow morning at 8 o'clock and give yourself a hand. It's a very long day.
If you think this was bad, wait till the chemist is the whole day.